Hello, it's Bill again. I've made another video on entropy, cleaned up from the last one, so we're going to go ahead and dive into this. What I've discovered is it appears like there might be a new second law, a universal law of entropy. In local systems, entropy increases or remains constant in idealized processes, but on a universal scale, entropy is conserved through the redistribution of degrees of freedom between cosmic and local scales. Now, we used to think that entropy could only reduce by reversing. So like if a broken glass were thrown or a glass were thrown on the ground and broken, somehow it would magically pop together again given the right circumstances. It's highly improbable. However, as we're going to discover, instead of reversing entropy, we are going to manage entropy by adding some here and subtracting some there. And we're going to do this by deletion and addition of degrees of freedom. And what it all comes down to is a change in entropy cosmic plus a change in entropy local equals 0. And here we have an example of, on the left side here, a new particle crosses an event horizon, the cosmic horizon. And therefore the local particles -1, but the cosmic horizon grows by 1 area. And here we have the opposite. We have local spin entanglement, and we need spins resolved. So the cosmic horizon emits a gravity bit, becomes smaller, and in a local particle emits a Hawking photon to conserve the energy. So we're going to get into the cases a little bit more here. You can see here that kind of describe what we had before. So this is the expansion phase where a local particle crosses the cosmic event horizon, causing this event horizon to grow. And in the other case, where the gravity bit is emitted from the cosmic event horizon to resolve spin entanglement measurements between entangled particles, and then those particles emit a Hawking photon to represent the now smaller cosmic horizon. And it might be helpful to organize how these particles exist in space by host particles, host space, host horizon, and guest particles. So here we have a green host particle, and this dimension from the host particle to its cosmic horizon is the green's host space at 13.8 billion light years away. Now here we have a guest particle. It was in green's local universe, but it crossed the horizon. And so its energy was encoded as negative energy on the cosmic horizon, added a Planck area of negative energy to grow that horizon. Now, we see here from the green particle's perspective, but what about the red particle's perspective? It's just reversed. So the red particle has the same distance to its cosmic horizon, and it sees that green is actually crossed red's cosmic horizon, adding 1 extra Planck area on red's cosmic horizon. Now you can see that both the red and the green particles see the same relative size and conditions of the universe, but they're out of causal contact now. The only way that they have any more contact is the information has been encoded on cosmic horizon. So now we're going to talk about how, when a particle crosses a cosmic horizon, how it becomes encoded as negative energy. So particles which have crossed have had their redshifted energy encoded on the horizon as negative energy bits. And what we'll see is we have an equation Eobservable equals Einitial divided by 1 plus z. So the z here is the amount of redshift. You've probably seen that in some astronomy videos. Einitial is the actual value of the spin of the particle, of the guest particle, that's while it's in the universe. So Eobservable means what the host particle sees. So the host particle sees the guest particle divided by 1 plus its redshift. That means as its redshift gets higher and higher, the observable, Eobservable, goes down and down. So here we talk about it some more. Eobservable is the observed spin energy value. The distant particle, also known as the guest particle, includes all Doppler shifted energy values. E initial is the energy of the guest particle expressed when local to the host particle. This value is the spin energy determined by the Landauer limit at the local curvature, and we saw that on my gravity video. Z is the amount of redshift, which is infinite at the cosmic horizon relative to its host particle. So when the redshift becomes infinite, when this particle crosses that horizon, then E observable becomes 0, because 1 plus infinity, E divided by infinity, equals 0. So then let's set the E initial to 1. Let's just make it 1 spin unit. So in this case, observable equals 0. We have 0 minus E initial, which is 1, equals minus 1. This bit of negative energy is only relative to the host particle and its host horizon. And this is how gravity is derived from negative energy. So now we got some information that we can talk about the Big Bang and cosmic horizon growth. So the Big Bang, 10 to the 122 particles are created by the very small cosmic horizons, 2 times 10 to the negative 18 meter in radius, which compressed the pairs of Hawking photons into matter particles. These new particles were dragged across these tiny horizons. And remember, we saw how when guest particles cross a horizon, it's minus S local plus S cosmic. So basically, during the Big Bang, we lost 10 to the 122 particles crossed our horizon. But because those particles crossed our horizon, we have all of this space. So we have the equation there. Change in S local minus 10 to the 122 particles increased the cosmic horizon by 10 to the 122 Planck areas, and we see that once again entropy equals 0. Every guest particle that crosses a host particle's horizon adds 1 Planck area to the surface of the host cosmic horizon, and that adds 1 divided by 2 pi Planck lengths to the radius of host space, which is the host particle's observable universe, as we showed before. So that 10 to the 122 particles that crossed, each one of those particles added 1 divided by 2 pi Planck lengths. And that's why we have the universe of 13.8 billion light years today. If when you have a Planck area increase, so every time a Planck area increases, every time a particle crosses, you get 1 Planck area increase, which increases space by 1 divided by 2 pi Planck lengths. And in the inverse situation, if your cosmic horizon loses a Planck area due to the emission of local gravity, then space shrinks by minus 1 divided by 2 pi Planck lengths. So I want to touch back again on the holographic universe. Every host particle has their own cosmic horizon, which contains information on all other guest particles which have crossed the host particle's cosmic horizon. This means each host particle includes a universe's worth of information on every host cosmic horizon. Guest particles are hosts in their own observable universes. Guest particles have their spins also encoded onto host particle horizons. And this means that every particle in the universe is both host and guest, and every particle is related to every other particle, connecting each particle with the universe worth of information. For entangled pair measurement, the host particle pays 1 unit of gravity from its cosmic horizon to resolve spin of its guest. So we had talked about how entropy conserves. So this means entropy must conserve at all eras of the universe. Now on the left side, we have a large young universe. 10 to the 122 particles zipped across the cosmic horizon, expanded this horizon to 10 to the 122 Planck areas on the cosmic horizon. We have 10 to the 82 guest particles inside, but the crossing from the early Big Bang is what made it. So all the entropy here is on the size of the cosmic horizon, and we have all of this nice space. But on a late small universe, this cosmic horizon has been emitting gravity locally over a very, very long time. And that cosmic horizon, every time it emits gravity, it reduces its radius of space by 1 divided by 2 pi Planck lengths. So here we see that we have very few cosmic horizon bits. It's only 2 times 10 to the negative 18 meters. So what happened is we discussed this before, that the Hawking photons are like receipts for every Planck area that was erased from a cosmic horizon. Nature emits a Hawking photon. So in the late small universe, you have 10 to the 122 Hawking photons, each receipts for each erased Planck area. So there's as many Hawking photons in this era as there were Planck areas of the cosmic horizon in the large young universe. So even though these two universes are vastly different in size, they have the same entropy configuration. And now we can calculate the total size of the universe. We had 10 to the 122 negative energy bits on each host horizon, giving us a radius of 13.8 billion light years. We have 10 to the 80 guest particles in each observable universe: stars, black holes, galaxies, you, me. So that means there's 10 to the 42 observable universes out of causal contact with our observable universe, each with 10 to the 80 guest particles in their own universe, each with their own stars, galaxies, black holes. So you can see it's 10 to the 122 divided by 10 to the 80 equals 10 to the 42. And since there are a total of 10 to the 24 stars in our observable universe, that means there's approximately 10 to the 66 unique stars in all observable universes in the overall 3D hyperstructure of the universe. So the implications of this: the universe conserves. Late era universe will compress Hawking photons. Hawking photons are emitted relative to a host particle and its host cosmic horizon. Conservation causes a big bang when the geometry of the host universe becomes small enough, compressing pairs of Hawking photons into having the Compton wavelengths equal in energy to a matter particle with a Compton wavelength of 2 times 10 to the negative 18 meters. So we saw this on the CMB temperature profile. That first hump is at 2 times 10 to the negative 18 approximately. And then the next two humps start at about 10 to the negative 15, look like quarks and gluons, and the next humps 4 and 5 appear to be electrons and photons. So cosmic horizons are pixelated per Planck area, but space emerges smoothly. And we saw this because each Planck area that was added onto the horizon added radius of 1 divided by 2 pi Planck lengths. So we have sub-Planck length space being added. So that's why space is smooth and the horizon's pixelated. And the universal geometry is a sawtooth waveform. When all those Hawking photons are compressed, they all turn to matter very quickly, and they very quickly cross those tiny horizons. There's very little space for them to cross, so they do it very quickly. So the universe expands in size very, very quickly. And then once it gets to that full size, it slowly starts getting smaller and smaller and smaller. So it has a very fast growth and a very slow shrinkage until it gets so small that, once again, it explodes in growth. So the size of an observable universe is due to the geometry of its cosmic horizon and not the apparent space dark energy seems to create. Dark energy does not create space. It shrinks it as now closer by objects will cross the host particle's cosmic horizon sooner. Space is the distance between a host particle and its horizon. And that's it for my video. I want to thank you for joining us. And if you have any questions or comments or any new discoveries, please let me know. Please look at my other videos and also read the descriptions. I got lots of good math in there. And have a great day.